Okay, YouTube, this is another example video of solving a nonlinear inequality in which we're going to look at a rational function here. And you'll notice that the first thing we did in our last video was made sure we got a 0 on the right hand side. Well, we already have a 0 here. What we need to do is interpret this as being some function of x, really, and saying, well, this is really asking if this function of x is greater than or equal to 0, and for what values of x it is greater than or equal to 0. So what we'll do is we're going to start actually by looking at the picture of this. So I have put in this equation 3x minus 5 over x minus 5 here into my calculator. I'm going to go ahead and hit graph. And I know this is some rational function, so we're going to get some vertical and horizontal asymptotes here. And we'll see if they're reasonable. But here's our rational function. It has two branches. And what I want to interpret first of all is where is this function greater than or equal to 0? In other words, where the function is greater than or equal to 0, that means where the y values are greater than or equal to 0. And where do these change? So I would say, well, first of all, just like in our last video, they change at zeros. So for instance here, it looks like we have a 0 at, between 1 and 2 here. I could zoom in to take a look at it. But the point is, we go from having positive y values on our graph to having negative y values on our graph at zeros. But you'll also notice that we're going from negative y values here instantly to positive y values here. So we have to recognize that critical values do not occur just at zeros. They also occur at asymptote values. So we could say, well, where is the vertical asymptote of this? We could count 1, 2, 3, 4. It looks like it's at 5. But that makes reasonable sense because the zeros of our denominator give us the asymptote values because that's where our function would be undefined at those x values. And likewise, we say, well, what's this 0 right here? We would say, well, it's the 0 of the entire function. And recall that when you're finding zeros of a function, you're finding the x values that make this true. So here's what we're going to do with rational functions. We're going to say, well, first of all, let's set this equal to 0. And we'll say, really, what I want to do is two things here. I want to find the zeros of the entire function, which would occur when the top of this equals 0. So in this case, we get 3x minus 5 equals 0, or that 3x equals 5, and that x is equal to 5/3. So we have a 0 at 5/3. So on our graph here, we could see that it was between 1 and 2. We could have zoomed in to see even closer. This is 1 2/3. I suppose we could write this again, 1 2/3. And you could even use a decimal that's repeating. And then also we want to find the zeros of the denominator because we say that's where vertical asymptotes lie, and we could change there also. Actually, I should write this as all our critical values here. This is all our critical value work. But just know that it occurs at asymptotes. So we say also at x equals 5 is a critical value. And you could even label this because there's an asymptote there. And we could even label this because there's a 0 here. And so what this does is, again, it splits up our number line for x values here into test intervals. I'll go 5 to the right, 1, 2, 3, 4, 5. But this is the same number line that we have on this graph right here. So I can already tell you just graphically by looking at this, we have positive y values from this x value here all the way to the left. Or we could say from all the way to the left up to this 0 right here, we have positive y values. And I also have positive y values to the right of x equals 5. Not at x equals 5 because it doesn't exist there, but to the right of it, I certainly have positive y values. So we already kind of know the x-axis intervals that we're going to indicate here, but it's, that's just to say that it's good to go look at the picture. We need to test this algebraically. So we'd say our intervals would be negative infinity up to this first 0 we had here, 1 2/3. I'll even write it as a mixed number. And then from 1 2/3 out to our next critical value, which is at 5 because we had an asymptote there. And then we would say, okay, from here out to infinity. That would be another test interval. So we'll choose representative x values here. I think we should mark these on the number line just because I think that's good practice. So we'd say 1 2/3, and I'm going to label this here just so I know that it's marked. And 5 were our critical values. So because I already know this one works here and this one works here, I'm going to put a little indicator up here. I think that these are it. But we want to test some values. I would say that 0 is as good a value as any to test into the initial inequality. So now, notice that I would normally say factor the top and the bottom, but they're already factored. And plug it into the factored form. But because it's already factored, it's going to make our job even easier. When we plug in 0, it looks like we would get 0 minus 5 over 0 minus 5, which would be this right here. But I would say that the point I want to draw upon is that we get a positive over a positive. Negative over negative is positive over positive. But we get a positive number, and that is greater than or equal to 0. So instantly, I'm going to put a box around this. And I'm going to say, well, between 1 2/3 and 5, I would say that I'm inclined to test 2 and just say, does 2 work? And so I'm going to plug it into the factored form. I get 3 times 2 minus 5, and this is going to be over 2 minus 5. greater than or equal to 0. So here's the important part. On top, I get a positive value. I'm just going to write positive. On bottom, I get a negative value. And I know that a positive over a negative is a negative, and a negative is not greater than or equal to 0. So I'm, of course, going to cross this off. Now, for the last value here, I would probably be inclined to test 6 just because it's right next to the critical value, and that's good practice. But I'm going to tell you, just because I already know the graph, I'm going to circle this one here. Just know that you have to show me this algebraically if you were doing this for my class. So the last thing I'm going to do here is color in the solutions. Now, the interesting thing here is we had a greater than or equal to. So that means that we should or shouldn't include the endpoints. Well, the one thing I want to point out here from our picture is this. It is greater than or equal to 0. So one might indicate that we're going to have to use a closed bracket or a closed dot on your number line if you're doing dots, solid or open. But basically, what I'm going to tell you is it is at a height of 0 at negative, positive 5/3. I was like, wait a minute. At positive 5/3, it's at a height of 0. So we have to include that in the solution set. So one way to check this would be to plug this into your function. But what I just want to point out here is this. Because it is a 0, you shouldn't have to plug it in. You know you're going to get 0 for an option. And what you get is some statement here that says 0 is greater than or equal to 0. So just know that at zeros, we would include that value. We would say this is in our solution set. And at 5, we're not going to include it. And one way to remember this is that we never, let's put a note here, never include asymptotes. We just don't do it. And the reason why really is because at 5, we can see on our picture here, it's approaching a height of positive infinity. So it's not at a height of 0. And so if it's not or equal to 0, we wouldn't include it. So our solutions, I do want to write our solutions here and we can just move on from this video. But basically it looks like we got from negative infinity all the way up to 1 2/3, and we included 1 2/3 because it was an or equals to situation in union with not including 5 all the way out to infinity. So again, find your zeros and your asymptotes. We could just say it this way. It's the zeros of the numerator and the zeros of the denominator. Split it up into test intervals, test them, circle the ones you like, and then check your endpoints. If it's a 0, keep it. If it's an asymptote, don't. Cheers.